Hello. Okay, it is time for lecture 4, but before we talk about the stuff from these slides, let us go first to the course calendar because we are here, and I want to remind you that this is here, that we don't forget about it. So in 2 weeks from now, when you're watching this video, hopefully on the same day, or maybe earlier, who knows, you will have a midterm, and that'll be your first one. So I'm going to make this page available, and here are some things that I put up at the top. Your midterm is going to be during the class time, so from 11 to 12:20 or whatever it is. From then to then is the only time that you will be able to take this midterm, so you have to be present either on GauchoSpace or Gradescope. I haven't decided where I'm going to post this midterm, but it's going to be one of those. And if you have any questions during the midterm, please just join me on Zoom, pretend it's like my office hours. I'll be available for the entire time from 11 to the end of class. Okay? You will need this one table for your midterm, and I'm going to talk about that in a second, how to read it and what to do with it, because it'll be also on your next homework. So this is the table of operator precedence, and we'll be using this later today. So you'll need that for your midterm. You can look at the rest of this page. Please read it. Here are all the topics that we're going to cover. I'll probably be nice, and we won't include things right up until the exam, like the lecture before, but probably 2 lectures before the exam, that material might still be on the exam. But I'll let you know. And here's like a study guide, some things that you can be doing to prepare for this, and you can expect to see all of these topics on the midterm in one way or another. And yeah, this is all stuff. I'm going to be posting the homework solutions here, so the first homework solutions are through this link, and here are some past exams from previous instructors. So please take a look at that, and hopefully it's helpful. But yeah, I will give you more information as I decide on which thing to use to give you this exam, either GauchoSpace or Gradescope. All right, so back to the calendar. I want to talk about something that's going to come up in your next homework, which is this thing called precedence. Okay, and you'll be using that page again on your exam. So let's see, I need to go to the actual book because that page is taken out of your book. So if I go to the table of contents and go to the end, there are some appendices in your book, and one of those is a table of the precedence of operators, it says. Oops, please go back. There we go. So you can think of precedence as parentheses. It's how parentheses get drawn around something. Think of precedence as the process of drawing parentheses around operations. Now, you already know how to do all this stuff from your like math classes, let's say. And give me a second because I forgot to plug my tablet in. Let me do that as I talk. So you know to do things like, you know your Pemdas Rules or whatever, however you say it these days, like first you do parentheses, then you do exponentiation, then multiplication, then division from left to right, then addition, and then subtraction. And you kind of like put those up into the same categories. So for example, once my tablet starts working, I'm going to draw. Come on, you can do it. There we go. All right, so for example, we have like, I don't know, x plus y plus z times 7. That's fine. So you know to do your Pemdas rules, right? To actually evaluate this, if I gave you actual values for x, y, and z, you know to do that. So the first thing that we see to do is this multiplication. That is, we say that binds tighter than the other operations. So first we do that kind of highlighting, parenthesization, and then we start doing the plus operations. We have 2 of them, and we'll work on those from left to right. So if we were to draw the parentheses here, we do it like that, and then this parenthesis is implicitly not necessary because it's just that big thing on the right-hand side plus that big thing on the left-hand side. So that plus that. All right, and that's how you'll draw those parentheses. But in C++, we have a lot more than just pluses and timeses, and even exponentiation. So going to this operator table, we have everything that you could ever do in the language of C++, including all these things like multiplication and division, all the things you already know how to draw parentheses for. But other things like cout stuff, and less than or greater than, equal to, ands and ors even, and assignment statements. So this is all necessary, and let me give you an example now with a bit more involved. So parentheses, let's draw the parentheses around x plus y again, times z this time, and checking whether or not that's greater than m minus 8, let's say. So in order to read the precedence table, you work from top to bottom. And higher precedence operations, we say they bind tighter. So you draw parentheses around, oh no, come back. You draw parentheses around the things that are immediately to the left and right of the current operand you're working on, or sorry, operation. Assuming that's a binary operation, like plus or minus. That takes two things on both sides. There are also unary operations, and we'll talk about that in a second. So for this, let's go to the precedence table and see how it's going to be evaluated. I think you have a good idea in your mind, but we want to follow this table now. So here are the groups of things. So everything in this group has the same precedence level, and you'll just look for any of these from left to right. So you go and you work down and you find the highest precedence group that exists in the thing you're trying to evaluate. And so I think if we go down this, the first thing that we see is the multiplication operation, and it's right there. So let's go and first draw our parentheses around the immediate thing to the left and the right of the multiplication operation, because that's what it means this kind of operation has higher precedence than other things. That's what that means. So look immediately to the left and to the right, find the smallest thing that you can put as the left operand and the right operand of the multiplication operation. Okay? So left and right operands of multiplication. So that's just terminology. And now let's move on down. So the next things that we see are addition and subtraction. Those are the next highest precedence operations that we need to parenthesize and worry about evaluating. So then we'll work from left to right, finding either pluses or minuses. And the plus is the first thing, so let's draw a parentheses around the immediate thing on the left and to the right of that plus sign. So it's going to be x plus this whole thing, y times z, okay? That's the next thing that's going to be evaluated, just like that. All right? And then we have the minus sign, and we'll draw immediately to the left and the right of it parentheses around those things, because that's what the minus sign is subtracting. It's the thing on the left from the thing on the right, and the smallest thing that you can take. Okay, and then the last operand, or the last operation we have not yet considered is this greater than, and it is all the way down here in looking like that. And so we know already, though, that the thing on the left is this whole thing, and the thing on the right is that whole thing. And you could draw parentheses if you really wanted to, but you don't really have to in that case. So I hope that makes sense. You're going to go down this list and find the highest precedence things. If they're in a group, you're going to find just the leftmost one and work on that until you find another. And all of these things have the same precedence level. And once you're done parenthesizing anything in a certain group, you'll move to the next one, see if you find anything with those operations. And you draw your parentheses again. So let's give a lot fancier of examples. Let's actually do the first one on your homework. So it is x equals 2 or y greater than 20. Or y is greater than 20. So we'll work our way down the list. What's the first operand or operation that we see? I get those words mixed up way too often. I think it is, it looks like it's the greater than sign because the equals is down here and the greater than is of higher precedence. It's up here. Okay? So let us then go and do the greater than first. All right, so we're going to draw parentheses around the immediate thing, the smallest thing on the left and the right, just like that. And then we're done with everything in this precedence group. So let's go down and see if we find anything in the next one. And yes, we have that equal sign, so we'll draw parentheses like that. And then the or is the last operation that we have not yet parenthesized, and it's way down here. And we already know what's on the left and the right of it, so I won't draw the parentheses in this case. Okay, one last really, really big one. And then hopefully it'll make some sense. So x plus 1 times 7 divided by 3 less than 0, and y minus z is equal to 7, or p is not equal to q plus 7. Okay, this is a big one. So let's find the first operation in any of these that is of highest precedence. And I think, I'm pretty sure it's going to be this group up here, multiplication and division. Okay, so let's do our multiplications and divisions from left to right. So that one. Oh, it looks like it's 1 times 7. And then we do division, that's the next one. So what's the immediate thing on the left and the right? That's this one divided by that one. The smallest thing that you can take at a time. Any other? No, we just have pluses and minuses now, which happen to be the next group. So let's worry about pluses and minuses now from left to right. So what's the smallest thing that I can put on the left-hand side of this one? Well, that's the x. And the smallest thing I can put on the right of the plus is this whole thing. Notice that it's not, for example, this whole thing. It's the smallest thing I can take. I guess I'll draw it in red because why not? The smallest thing I can take. And then pluses and minuses, and then pluses. Okay, continuing. Then we don't have any of these. Let's look at these ones now. Any relational operators? Yes, we have a less than. So smallest thing on the left and the right. And nothing else, just equals and not equals, which are of lower precedence. So those are down there. So let's do the equalses. So the smallest thing that I can put on the left and the smallest thing I can put on the right. And the not equals, smallest thing, smallest thing. For example, it's not this whole thing and that whole thing, or anything like that. The smallest thing I can put on the left and the right of these operations. And now, the only things that we haven't touched are these ands and ors. So this is actually quite useful to know how these are parenthesized, so that you don't have to always put in the parentheses. And we say binds tighter than or. So even if the and was on the right-hand side, we would be worrying about that and first. So the and goes first, so the smallest thing I can put on the left side and the smallest thing I can put on the right-hand side of that and. So that is how you would draw the parentheses in this case, and then or is the last thing. On the left, you have this entire thing, and the right, you have this entire thing. And now that you know how to draw the parentheses, you should also worry about evaluating these operations, because you know the orders of things now. So for example, if I were evaluating this particular expression, and I gave you actual values for things, like for example, I don't know, let's say x equals 1, y equals 2, z equals 3, and m equals 4. Well, this would evaluate to, well, it's y times z. It's 6 plus x is 1, so that's 7. Is that greater than m minus 8, which is 4 now, 4 minus 8. So that would become that, which would become 7. Is that greater than negative 4? Yes, it is. So this entire operation would evaluate to in C++? True, right? Because that's what a greater than is going to return. It's going to return a Boolean to you. So yes, true. That is the final answer. And if I change these numbers around, like if I made these all maybe negatives, x, y, and z, then this probably would end up being false. Okay, so understand how you might use this kind of parenthesization to evaluate an expression, to get a final answer. If it's a number, it's just an integer. If it's a Boolean expression, in the end, it's true or false, right? So we've also, we've talked about nothing but binary operations. So a binary operation takes something on the left and the right. A unary operation only takes one operand. And you already know a few unary operations. One of those is negation, so negative x. It only takes one thing. You can think of it like a function. So like negative x, or not, the not operation, not y. And those have their own precedence levels. They're up here. Here they are. The not and the unary minus are all of the same precedence level. So this gets parenthesized in a certain order. Like, I don't know, let's say it was that for some reason. You'd parenthesize that, and then the greater than is different. Okay, so I think that's everything that I wanted to talk about for precedence. It will be on the midterm, so please study this and do your homework on it. Hopefully it'll make sense after you do your homework as well. And yeah, so we've talked about the midterm. Let us now continue. Let's go to the slides for today, and let me get rid of all of this stuff from last time so that we can make a brand new folder for today. So today we're going to talk about functions some more, as well as something called test-driven development, and also get some more examples with loops. So I encourage you to go through like we did last time on this slide and convince yourself that all of these things are going to be infinite loops. Remember that this last one is quite tricky because this is an assignment operation, and an assignment just so happens to return the value of the thing that you're assigning. So this entire expression evaluates to the right-hand side of the equals, which is 2. So this whole thing is like saying while 2, which is true after it. And it'll also do the setting of y, as well as return 2. And here's a new question for you today. So please take a second to pause the video and come up with your answer, and then we'll talk about it. Okay, so let us, I guess, I could probably make a piece of code quite quickly to do this. Let us do it. Okay. Why not? Let's make a new folder for today. I'm going to go a bit faster now that we know how to do all of this. New lab folder. No, not lab, sorry. lec04. Getting ahead of myself. Move lab04 to lec04. There we go. lec04, and let's make a new file called loops.cpp, and let us go on into that. So can I take a bit from last time? Most of these are probably going to end up being the same. Okay, here's a bunch of stuff from last time. Let's see how different that is from what this code is saying. That is quite different. Let's get rid of it then. And let's see how well we can copy and paste. Feel free to skip ahead as I copy and paste all of this. That's all I'm doing. So if you look at this code, hopefully you have a good idea of what it's gonna do given a certain value for n. That is a very good skill to have, just looking at coding, knowing how it's going to execute and be evaluated. All right, let me make this a bit prettier, and then we'll talk about it. Let's see here. All right, so this is mostly looking good. All right, so here's a for loop, and it starts out, well, let's give a certain value for n. Let's say n is like 5. So it'll go from 0 to 4, because that's strictly less than 5, and output the number. So it'll output 0, 1, 2, 3, and 4. Okay. This one will essentially do the same thing, because start out x being 0 while it's less than 4, or while it's less than 5, so it'll go between 0 and 4, it'll print it out, and then increment x. So print out 0, 1, 2, 3, 4. Then this again will, x is 0, print out 0, make x 1, then it'll be 1, come back. When it is 4, it'll print out 4, make x 5, and yeah, 5 is not strictly less than 5, assuming n happened to be 5, and we'll stop. So it looks like if n is 5, this will all do the right thing. Let us see. Let us watch it work. Let's go to this, and g++ loops.cpp-o loops. And oops, what have I done? Oh, I've redefined x. Excuse me. We can only have one x in the program. So let us cheat, and instead of x here, let's say I could just get rid of the declaration and reset x to be 0, or you can just call this y. How about that? And then we can run loops. And it looks like it's doing the same thing each time. Let's actually separate these. Just like that. And that's a bit cleaner now. We can, oops, I forgot to put another one right here. That should be a little bit cleaner. Now I can see the difference. All right, good enough. All right, so now the question is, do-while loops are a bit different because they always do their body the first time. So can we trick this into doing its body once, but never again? And that the answer to that is in fact yes. So I make this -5, x starting at 0, x will always be greater than -5, won't it? So this loop will never execute. Same with this one. But this one will always do the body at least once. So we should see -5 printed out just for the do-while loop, but not for any other loop. And then the do-while loop will also stop, because then it goes to check its condition. No, sorry, it'll print 0, because that's what y happened to be, sorry. So then y will become 1, but yes, 1 is less than, 1 is not less than -5, so the while loop, the do-while loop will stop. So that is the case where these loops are in fact different. The for and the while are the same, but the do-while loop is special because it always does its body once, even if the while condition is immediately false. Okay? So the answer is in fact C here. Let me go ahead and circle that. Oh no, not highlight. Oops. And it's not letting me undo very easily. Let's go here. That's the real pen. All right, so the answer is C, and I hope that makes sense now. Please look at the code. So now we've talked about functions last time, just as a brief overview, and we'll get some more examples today. But functions help you abstract your code, and it helps keep your program, this is an acronym, DRY, stands for don't repeat yourself. So DRY equals don't repeat yourself. So if you have something that you keep doing all the time, you should make a function to abstract away doing that thing, so that you only just have to call a function as opposed to write a million lines of code to do that same thing over and over again. So there are 3 things that you do when you use a function. One you can skip, but we'll talk about it. We'll just keep doing it today. You declare the function, you define the function, and then you can also call the function. There's 3 different ways you can use a function, and it all culminates in you actually calling that final function that you made for yourself. Okay. So here is a problem that is very similar to the one that we worked on last time, and we're going to change our code to use a function instead of just writing everything in the main function. Okay, so we're going to make a new function to create or to solve the problem of summing these things together, and then we can worry in the main function about printing this out, perhaps. All right, so let's go to a new file. Let's call it some series again. .cpp. And let's actually take everything from last time's sum series and copy it in. So the idea here is this whole sum calculation, let's make this its own function, okay? So let's make a function called sum. That sums the series for us, given a certain n. All right? So all this stuff from last time, this all belongs in the main function, but this is the stuff that we can take out. Okay, this is the stuff that does the actual summation process. So let's bring it out for just a second. We'll put it in a real function in a second. And then what we want to do down here is, instead of just cout sum that we built up, let's cout sum of n. Okay, and let's also make it pretty so that we print our. Let's see here. Is it from like 2 perhaps? There it is. Oh, I can't remember. I'm just looking for the code that makes the printing out the doubles pretty. And I don't know where we'd put that. That's okay. Let us go back to this code here. And so we do want to print out some of the first n terms is, and then a colon. Why not? And you can make this prettier by using that fixed point and things from last lecture. Now, so yeah, we're going to print out the sum now, and our job now is to make a function that actually sums the series. So let's declare the function. Let's declare the function, which tells us what it does and what it returns. So this is going to return back the sum, which is going to be a double, right? And we'll call it sum, and it's going to take the number of terms to add together, so that n, okay? N is a parameter of the function. And it's also going to be a command line argument. And what is the type of n? It's an integer. And so now we can, oh sorry, I just want to declare the function at the moment, so I'm not going to put the braces. So this is the function declared now. And because you declared it, you can actually put the code below main to make things prettier. So let's define the function here. So we're going to take the declaration and put some braces around it, and actually provide an implementation of the sum function. And inside, we'll do all of this work. And remember that when you're writing a function, let's call this s instead of sum. S. When you're writing a function, you have to give back the value. Give back the final result to whoever called us. And giving back that final result is returning, right? So we return the value of s, which will hold the sum. S will hold the sum. Okay? So with that, we've just declared the function. We have defined the function. Here's the definition below. And here, we call the function. We ask it to compute a value for a certain value of n. So call the function sum below. And with that, I think we should be able to run and make use of this function. So g++ sum series -o sum series. Oh, I need to give it a value, so let's say 2 and 3. All right. And remember, you can set the precision and do all that cool stuff, but I forgot where that code is, and I will leave that to you. Okay. Now, let us do the same thing as last time again, where we draw a square, but let's use a function instead. Okay? Let us take the stuff from the draw square from last time again, and we'll make our own version of it here today. Oops. Copy, paste, call this, I don't want to call it draw square, but I want it to live in our lecture 4 folder. Okay, so again, the process of drawing a square we will extract from the main function. We'll make a function called draw square. We'll declare it. We'll define it down here below the main function. And we'll call it here in the main function. Let's get rid of some of these comments from last time. Call the draw square function to help output the square itself. All right, so all this stuff, the stuff that we use to actually draw the square, we can take out and put it down here in the definition eventually. Let's actually make draw square a function that returns a string so that we can see out the result of calling the draw square function. Okay, just like that. So draw square will return a string. Your other option was to have it actually print the thing, and it would then be a void function that you could call, just like draw square of n. But let's have it return a string, because that'll help you for your next lab. Okay, so let's make our draw square function, and let's say it returns a string. I'll also include the string library, just to be safe. String draw square, and a square of a given width, which is another integer parameter. Okay, and I don't want to define it just yet. I'm getting ahead of the game. So this is just the declaration. This is all the compiler needs to know to generate code for an eventual draw square function that takes an n and returns a string. Now it knows how to use it down here. And so here we can define it by putting some braces around actual code that does something. Okay. Now, because I want this to return a string, I'm going to build up the answer not using cout, but using some intermediate value. So string result, let's say, equals the empty string. And I'm going to add to this string, keep adding up characters into this string. Okay, so instead of saying cout a star for the current star I'm trying to put in my square, I can say result equals result plus that star. Okay, and again for the new line I say result equals result plus that new line character. And remember, there's some shorthand for this. You could say plus equals instead of that to save you some typing. And so now our actual star, or our square, excuse me, is our square of stars is stored in the result variable, and we need to give that back to whoever called us. We'll return result. Okay? So with that, now we're able to call this function draw square. It'll return to us a string, and cout will output that string as well as a new line. Okay? And it also looks like this function wanted us to use cin instead of command line arguments, so let's work on that. That makes our lives a bit easier. Let's not get a number there. Let's get a number from the user instead. So we'll cout enter the width of the square, and it looks like it wants us to output a new line because we want the user to input the number on the new line and not the same one. So let's output a new line, and then we can get the number using cin. So now we have our n, get the width from the user. Okay, so now we have our cin, getting our n, and then we'll draw the square with our n, and here is us using that, defining the function that will be used right here when we call it. All right, so this should, in theory, be okay. So g++ draw square -o draw square, and let us run it into the width of square 5, and then it outputs a square of width 5 and a few new lines. So again, this is returning a string when we call this function. That string is being given to cout to actually do the final printing, and then we also print a new line. So main is doing the printing, but draw square is doing the construction of the string to print. I hope that makes sense. Okay, let's keep on moving here. So here, I think, yes, I just want to use this final example to talk about a few different things. Okay, let me get some water. Let's make this very simple program that sums together things. So we'll make like a sum function and then have our main function as well, okay? And let me call this, I guess we can call it sum, but I want to do a lot of things with this. So let's just first call it sum. Why not? Sum.cpp. Okay, include iostream using namespace stt. And here's what we want to do. All of this. We just have a very simple sum function. And oh, why did that get put right there? Very odd. Okay, put that like that like that. That's more or less as pretty as it's gonna get. Okay, and do that as well as that and that and that. Okay, that's pretty enough. We'll also return 0, of course. So here's our sum.cpp file, and I'll eventually run this. So let's talk about how our programs are actually being run when in like actual computer memory. And a new term for us is what's called the runtime stack. So a stack is a place in memory that each function, when we call it, lives. So every time a function is called, we make a new region in memory. We make a new what's called stack frame to manage the local variables of that particular function. So every time we call a function, its local variables are made on the stack. So you can have multiple calls to the same function. If maybe a function calls itself, those will have separate copies of local variables. And when a function returns, we remove it from the stack, and all of its memory, which includes its local variables, go away. So local variables, they get created and deleted on this thing called the stack, and using this last in, first out principle. And let's talk about that. So in theory, we want this to print out the sum 30, right? Print out 30. And we want to do that by calling this intermediate sum function. So let's talk about the stack. All right. So the very first thing that happens when your program is run, we make a stack frame for the main function. So this is a graphical diagram of the stack. So here is our main function. Okay, this is our main function. Let's say, let me write some things about this. So this is main's stack frame. Inside of it live all of its local variables. When main calls other functions, those functions get their own stack frame made for them to to store their own local variables. So for example, main has a few local variables. It has result, x, and y. Okay, those are the 3 variables that main has. And so I will make some boxes inside of main stack frame to represent those. I'll say x and y, and I'll just use res here because I didn't give myself enough space. And those start out being, let's see, 0, 10, and 20. All right, 0, 10, and 20. And then when main calls the sum function, okay, when main calls the sum function, we add a stack frame on top of it. And the stack is like, it's a stack of papers, say. And it grows and it gets bigger. So here's the sum stack frame. So this for the sum function. The sum has 2 local variables because parameters count as variables. Count as local variables as far as the stack is concerned, because the same function could be called with different arguments. And if we didn't save those separate arguments, we wouldn't know how to do something different. So the sum function has a and b, and what's going to happen here is we're going to make space for those in memory, a and b, and I think they're x and y. So in this case, we'll get x and y copied into a and b. These are separate places in memory. X is 10 and a is 10, but those are different places in memory. Okay? And so this will, when we call this function, it's going to do something, and then it's going to stop. So once this function returns, the sum function returns, we get rid of its stack frame, and we're now back in main. Okay? When a function returns, its stack frame gets deleted, and the function below it, because always the function below it is the one that called it, on the stack, that is the function that called it, gets the result, if there is one, and resumes its own execution. So the idea is, when main called this sum function, we immediately stopped executing the main function, and we went up into the sum function to start executing that. Sum did its work, and we ended up finishing the sum function, popping it off the stack, we say, and sum is a void function, so it didn't give any result back to the main function, but it gave control of the program back to the main function, and oops, the main function that was sitting right here, waiting for this value, can now store the value that it got back, which, oh man, there was an issue here, and do the rest of its work, because the sum, the main function was waiting right here for sum to complete its operations. Okay, that is essentially what the runtime stack is doing here. And last in, first out just means this. So last in, first out means that the last thing added to the stack is the first thing that gets removed from it. So like sum was the newest function to be called, and once it returns, it's going to take itself off the stack. It was the first thing to be removed. Okay, that's all that means. So that is the runtime stack in a nutshell. And now, given everything I just did, tell me what you think the output of the following code should be. Oh, sorry, no. Let's go back to this one, because this is doing something weird again. So here, a plus b is printing out the answer instead of giving it back as an integer. So something's going to go wrong in this case. We're going to print out a plus b. We're going to print out 30 because a and b happen to be 10 and 20. So we'll print out a and b, but the integer that's returned here, there isn't one. So this is what's called undefined behavior, and we're going to get some random value into result. Okay? And once we see out that, we have no clue what it's going to be. It's random. Okay? So we need to fix this function for sure. G++ sum.cpp-o sum. Yeah, even your compiler will even warn you about this, but it'll let it compile. So we output 30, and then it seems that it just so happened to be returning implicitly the number 0, but that is undefined behavior. You cannot count on that to happen. It won't always be this nice number like 0. All right? So we need to fix this for sure. We need to give back the answer instead of just printing it out. There is no return here. We'll get what's called undefined behavior. So any possible value is returned here. It's random every time, and you can't count on anything. So undefined behavior means that just whatever value was sitting around in memory where in the location where the return value was supposed to be is going to be what's returned. That's all. So we need to fix this, of course. Let us fix it. Here is a new sum function. See if you can figure out before I code it up what should be the output. Maybe take a second to pause and see what you'll think. So that is fixing this. I'll make a new sum2 maybe, .cpp. Now, instead of all of this, we're going to return a plus b. We're going to give back the answer. All right, result equals sum xy. We're going to see out results. So this is looking good to me. I think it'll return, this will return 30, and it'll output just 30. So this is sum 2, output as sum 2. And, oh man, does it do it right. And let's talk about why this code works. Okay, let's draw the stack again. So when our program is called, the terminal calls the main function, we can think of it. So here's our main function. I'll just say main like that. And again, we had our x and our y and our result variables, which I will call res for space reasons. So those started out with certain values. Results started out as 0, and x and y were 10 and 20. All right? 10, 20, and 0. And then, when we were outputting, or when we were doing our work, we then said result equals sum xy, which is immediately going to do the right-hand side to get a value to eventually put into result. So we're going to call sum xy, and calling makes a new stack frame. So we push onto the stack sum. So we're going to call this function with certain arguments, and those arguments were 10 and 20 given as the values of the parameters a and b. A and b happen to be 10 and 20 here. Okay? And now sum actually returns something like it was supposed to all along, because we said it was returning an int. So it returns a plus b, which means it returns 30. So it's going to give back 30 to main before removing itself from the stack. Okay? That's the process of calling a function and having it return something. So it's going to give back its answer to main. Okay? So it's going to say result equals 30 now, because that was the result of the call. So now result, not anymore is it 0, it's now 30. And we'll see out 30 and end the program. And essentially you can think of the program ending as main also returning to, say, the terminal. Okay, so that is that entire process, and I hope that makes some sense. And that just goes to show that there's a big difference between printing and returning something. When we print, as in up here, sure, we will print out the final answer, but we don't actually give back anything, okay? Returning means that we give back an answer to who called us, so that we can maybe replace the sum xy with 30. When we did not return anything, we got a random value, and sum xy was meaningless, okay? So that's the difference between printing and returning. It's a very big, big difference, okay? And then finally, take a guess as to what's going to happen here when we call this function. So remember that the exit function is defined in C standard library, the cstdlib header, this one up here. If you can't see where my mouse is, that one. It has the exit function, and you can call it, and it will end the program, okay? So let's see what happens here. So first we start out result at 0, x and y being 10 and 20. So again, we're looking like this. I actually want to start this way down here. Yeah, that's much better. All right, so here we have main. Really, res should be over here because it's the first thing made, x and y. 0, 10, 20, and then we immediately call, well, we eventually call the sum function, right? Result equals sum xy, so we go into the sum function, we call it with a and b being 10 and 20 again. A and b being 10 and 20, and sum also this time happens to have a results variable, so we'll make one for it, and again I'll just call it res because I don't have a lot of space, and it will store the sum of a and b, which happens to be 30, right? A plus b is 30. And then immediately calls the exit function, which stops the program. So sum never returns. The entire program at this point just ends. Nothing gets given back. The program just stops. Okay, because that's what the exit function means. Just stop the entire program. Don't continue anything. So we never return back to main and print anything out. The program just stops. Stops completely. Okay, I hope that makes sense. So that is the end of our slides today. But remember, I said something about this thing called test-driven development, test-driven code development, or just test-driven development. And I want to use this sum example to talk about that as well as separate compilation. So let's do a few things. Let's first talk about this thing called separate compilation. So you will eventually write very large programs. It's important to keep these in order, and you don't want to write very long files, so it's better to split up your program often. Split up your program into multiple small files instead of one big one. This topic called separate compilation is the process of splitting up your things and still getting a final compilable result. Okay, so we'll come back to this. Or you know what, let's start out doing it. So let's make a new folder inside of Leco4. Make directory for separate compilation and TDD, because why not? TDD stands for test-driven development. I'm going to go in there. All right, so here I am inside of that folder. I'm going to take a sum function or sum program with me. This is the one that works. So let's make bear with me here. Let's make a sum.cpp inside of our new separate compilation and TDD folder. All right, sum.cpp. And we're going to eventually split this up into multiple files. So to start out, let us make a declaration for our sum function. So we can put it below. All right, int sum, int a, int b. So now I have a declaration, an implementation, and a main function. So let's split this up. Let's create a library for our sum function, just like we have IOStream. It's some library with a bunch of functions that we can use, like cout and cin. So let's make a library for our sum function to hold our sum function. Okay. So the idea is, let's put it down here. Let's put it in a file so we could say, like, include sum dot dot dot. There's a special kind of file name that you need here. And now we can place sum into its own file. We make two, actually. Let's see here. I shouldn't have called this sum.cpp, but this is going to eventually work out, don't worry. So the idea is sum.cpp will hold the actual sum function, and we're going to let the library be implemented inside of our sum.cpp file, and our main function is going to go somewhere else. Okay, so using sum library.cpp. So this is the idea. We're going to do this so that we can include the sum library, and we don't actually need to include IOStream or anything else. All it needs to happen in this final program. And so the idea is we're going to make a library to hold our sum function so we can include it, and then that's where that lives. That's where the sum function lives, and we can call it. Okay? So this requires one extra thing, and that's called a header file, sum.h. And that's where the declaration lives. Okay? So I've just made 3 files. This is useful when you want to build your own libraries. So I've just made 3 files. The first, use sum.cpp. And then I've made sum.h, sum.cpp. Let's talk about these kinds of files. This first one is like the normal file that you've already written. This is the file with the main function that includes the sum library. Okay, so that's exactly what we know. We're just going to include the library and use it. Sum.cpp is where the implementation of the library, of all the library functions live. Subject-verb agreement. So where the implementation lives of all of those library functions. And sum.h, this is new. This file includes all the declarations of the library functions. We split that up so that we can all we have to do is include sum.h now, as long as we compile with sum.cpp. We include sum.h and compile with sum.cpp. And I'll show you what that means. Done. And .h stands for a header file. The .h stands for header file. Okay, that's where these declarations are also called headers. Okay, so that's where the declarations live. Some library declarations. And this is the sum library implementation of all the functions. Maybe we had multiple. And then the idea is we'll include sum.h. We include the header file, which only contains the declarations. So we need to give the compiler the actual implementation, though, which lives in sum.cpp, because if you don't, it's just going to complain. Where is this implementation? I know that there is a sum function that exists, but where is it? I don't know what to put here. I don't know what code to put here. I know that it will be type correct because I know that the sum function exists and it has an a, it takes an a and a b and returns an int, so the use of it is correct, but I need to know where it lives. So the first thing, let's show an error. So G++, using sum library.cpp-o, using sum library, I guess. This is going to complain to us because it's going to say, I don't know where this sum function is. It's actually a linker error because it is not able to combine all the code properly. Otherwise, you'll get a linker error. So you need to, so just compile with G++ using, well, let's actually copy this. That's a lot to type out. We need all of this still. But we also need to compile with sum.cpp. The sum.cpp is important. Okay, so as long as we do that, we're home free. Because by including sum.h, we know that the sum function exists and it's able to compile this file into code. But when it's time to link the program, then it needs to know where this sum lives. Okay. Okay, and then it'll work. We can call this program using sum library, and it'll actually do the thing. Okay, so this gets compiled into, oh no, my computer is going very slow right now for some reason, into use sum.o, we can say. It's a special compiled file, and eventually we'll talk about this when we get into makefiles. This is compiled. Oh no, my computer is going super slow. I'm sorry about this. I might have to restart this. Compiled into sum.o. And this is where, so this is the compilation process. It compiles these two things into machine code. This is machine code. And then the linker takes care of bringing them both together, all of their implementations, into the final executable. And that's the program you can actually run. And that is the linker, the linking process. It brings together all of those separate compiled implementations into one final program. Okay, and that's why we got a linker error, because we didn't include the compiled version of the sum function. Okay, so that is separate compilation in a nutshell. And the last thing that I want to talk about is test-driven development. So, test-driven development. Okay, or TDD. So TDD is about writing tests before you implement anything. Okay, so we write something called a test, or usually multiple tests for a certain thing, and that's how we can be confident that what we're about to write is correct. We write a bunch of tests for example, the sum function. So that we know, so that we're confident that once it passes the tests, that it is correct. Okay, that's the idea. So you can make a bunch of tests. Like here's a good test for the sum function. Test 1, maybe. We want to test that calling sum with 0 and 42 is equal to 42. And maybe test 2, we can say that calling the sum function with -5 and 5 is equal to 0. And at that point, we can be pretty confident that it's actually doing the right thing, and not doing, like, I don't know, like returning the right operation, or the right parameter. Okay, so that's the idea. So we make the tests, like we write the tests that check for these kinds of things before we actually write the code. So let us do that using some library. Here, I will make, let's see here, instead of a normal main function, this will be my test program. Let's write a bunch of tests for our sum function. So we want to make sure that test 1, sum of 0 and 42 is equal to 42. And then test 2. And the idea is we write this before we actually write the implementation of the sum function. Like, we don't know what it needs to be. So let's make it incorrect first. So return B, for example. This is just a stub. We call it a stub now. It's a small implementation of this function that compiles but is incorrect. So if you ever have a very large function that you want to write and you want to just get everything compiling, you can write what's called a stub like this. Just needs to return an int. We could just say, okay, return 42. Sure. And so it'll compile, but it'll be incorrect. And then we want to write tests that make sure that it actually does the right thing. So here's 2 tests, and we want to make sure that this all works. Okay? So here's how you write a test. You can say, you can just use an if statement, really. If sum 0, 42 is not equal to 42, see error, because this was an error, test 1 failed, for example, new line. And you can also stop the program if you really wanted to. That wasn't good enough. And here you can say, like, test 2 failed if sum -5, 5 was not equal to 0. So notice that I'm negating. Like, it was correct if it was equal to 0, but if it's not equal to 0, then it was wrong. Okay? So that's how we can compile and run this. And right now, remember that I made this incorrect. So this, actually, let's make it super incorrect. Let's make it return 43. So now neither of the tests will say passed. Okay? Else, I don't know, see error, test 1 passed. this is test 2. So now neither of them should pass, right? Because I have it returning 43. Yeah, so they both failed. Okay, let's fix one. Okay, this is a more accurate implementation, at least in terms of our tests. If I recompile and rerun, oh, now test 1 passed and test 2 failed. And that's why it's a good idea to write as many tests as you can reasonably handle. It's a very good idea to write as many tests as you can. Because maybe the first one passes, but the second one fails. Okay? Because they test different properties of the function. So now we can make this correct and watch all of our tests pass and run. All right, so now we have these tests and they passed, and we're confident now that our final implementation of our sum function is correct. And the idea of using test-driven development is you write the tests at the very beginning so that you know exactly the kinds of properties that your sum function needs to have in order to be correct. Okay? And we can also, and you'll see this in later labs, we can take out these testing things into functions that look a bit more fancy. So we can include something like tdd.h, and that will include test-driven development things. But for now, let's make our function that does tdd up here. Let's see here. The most common function that you will use in your future labs is something like assert true. So let's make an assertion function. It checks, that is, asserts that a certain Boolean valued property was true. And that's essentially abstracting away this kind of thing that we've been doing. So it'll be a void function. We can say assert true and string name of test, and then Boolean value to assert true, or property, let's say. And then we can implement it. We could say if property is false, which is equivalent to saying if not property, right, is true. So if property is false, we're going to err test failed, and then we'll give the name of the test. Otherwise, it wasn't an error, so we can say cout even. Test passed. And we'll give you some kind of assert true function in your future labs. Okay, well, that's the idea. And now we can just say assert true. And we can give this a better name as well. So we want to make sure that this happens to be true. And so we can get rid of that whole negation that we were doing ourselves. So assert true that the sum of this and that equals that. And this could be sum 0, 42. That can be the name of the test. And this could be sum -5, 5. That can be the name of the test. And then the property is the thing that we want to check and make sure happen to be true, because that means that we have a good implementation on our hands. Okay, so that's the idea there. And I think with that, if we go and compile and run this, we should see essentially the same thing. Oh, I forgot a semicolon right there. Excuse me. Test passed. Each of those, and that's beautiful. And if we make this wrong again, return 43, then we should see it not work. Test failed. Cool. And now we can make it work again. And again, we can package this assert true function into its own library even. Okay? Let's make a tdd.h and a tdd.cpp.
And instead of doing this, oops, let's keep that compiler as well. Or that comment. So there's that. That's the implementation of the test-driven development function, the assertion function. This is the declaration of it. And here is us using it. And in order to use it, we need to also include sum.tdd.h for the sum function for the assert true function. And so we need to also give the compiler tdd.cpp. Okay. Let me make sure all these comments still make sense. Also make a library for test-driven development related functions. Implementations, plural. And that's exactly what you want to do when you compile. Otherwise, you'll get linker errors. And again, TDD means writing these kinds of tests before you actually write the code itself. And I was using the old one without including tdd.h as well. tdd.cpp, sorry. That's where the implementation lives. And now everything should be fine. Oh, except for here in the TDD implementation, I was using carr, I was using cout, and those are compiled separately to the main function, where I included iostream and namespace std. That also needs to be done up here. Okay? That is the key. All right. And you can also get a bit fancier by including this in the .h file even, and doing this. So here are where all of my declarations and includes live. I can also include tdd.h in the tdd.cpp file. So this will now copy and paste, essentially, this entire file. So that's essentially what inclusion does. Inclusion, a file, copies and pastes its contents. Okay, that's quite nice. So there's an iostream file somewhere that's being copied and pasted for you. And we use normal quotes for files in your current directory, and these kinds of angle brackets for library files. Okay, in case that wasn't clear. Oops, come back. So that's the kind of thing that we could be doing, especially if we had a bunch of different functions that called it themselves. And we could do this for sum as well, like sum.cpp. Can also include sum.h in case we needed to include like iostream or anything for that particular library. Okay, so now inside of tdd.cpp we're copying and pasting the tdd.h file, which will then give us access to cin and cout and using iostream and namespace std. Okay, that's the reason we did that. And now when we finally compile, we should be home free and we can actually run this and our tests pass once again. So we just split our implementation up into many different files. So this is now spring 2020, code from class, lecture 4, this folder. We have a bunch of different implementation and header files, and we bring them all together in this final using some library .cpp file. Okay, that is, I think, everything I wanted to talk about today, so I will see you next time.